This is Mr. Antrim, Honors Chem, and this will be a ChemCast on bond polarity. It's section 9 from your chapter 9 study guide. Bond polarity, you will see, and as you continue on in chemistry, is a very important concept, and it relates to what we've been studying about molecular geometry. First of all, we're going to define electronegativity. You might recall that is simply the attraction for a shared pair of electrons. There's my symbol for electrons. What that means essentially is if we have two elements, let's just say hypothetical element X and element Y, and these would be two nonmetals, and they're sharing a pair of electrons. That's a chemical bond, a covalent bond, as we have learned. So to fill in some of these blanks, it says these electrons are in overlapping orbitals between the bonds, between the bonded atoms. This pair of electrons may be shared equally, and this is very important. These two electrons may be shared equally, and this is called a non-polar covalent bond. It goes on to say if the pair is not shared equally, then it is known as a polar covalent bond. Bond polarity has a very significant effect on the properties of a molecule. So what this means is that these two atoms, even though they're sharing these electrons, they're not necessarily sharing them equally. If atom X is more electronegative, has a greater attraction for electrons than Y, these electrons are going to be pulled towards this element X. So maybe they would be, we could almost represent it like this, that they're closer to X than they are to Y. This would be called a polar bond. Again, if the electrons are shared equally, because these two elements have the same or very similar electronegativities or similar attraction, then the electrons aren't going to be pulled one way or the other. They're going to be shared equally, and again, that's a non-polar covalent bond. To determine the bond polarity, you must know the electronegativities, and I'm just going to abbreviate here, and you can write it out on yourself by yourself. The electronegativities of each of the two atoms involved. A table of these, and you're going to have to refer to this, is on page 263 of your textbook. Just a couple of review items. Remember that electronegativity actually increases as we move from left to right on the periodic table. This is because atoms will be are getting smaller, you might recall, as you move left to right. And as you recall, you can fill the rest of this in. Large atoms do not attract electrons as much as small atoms because the outer shell is much farther from the nucleus. So small atoms, which are going to be found on the left side of the periodic table, and closer to the top as you move up, small atoms have higher attraction for electrons. This table 363 actually provides values for these attractions. If we look at the next page, again, a lot of this you're going to have to go back and fill. It says, in general, the difference in electronegativities, called the electronegativity difference, we're going to abbreviate that as E and D. Anytime you see me refer to that. Electronegativity difference between the two atoms. If it is very small, then the two atoms must be sharing electrons fairly equally, and thus would be nonpolar. If the electronegativity difference is very large, then they're sharing them unequally, and we would probably refer to this correctly as a polar covalent bond. We will use the symbols partial negative, we'll use this delta sign, it's a lowercase delta in the Greek alphabet, delta negative, and for positive we'll say delta positive. The reason we're not going to say positive and negative is because we're still dealing with covalent bonds. Electrons are being shared, so an electron isn't going to be transferred. If that was the case, you would end up with ions, full positive, full negative charges. In this case, one side of the bond the sharing, for example, in this scenario here. If X is more electronegative, the electrons are going to be around, they're still sharing, but they're just going to be around here more than they're going to be around the Y. So we would say, let's give this a partial negative and a partial positive here. So when you see this symbol, it refers to partial positive and partial negative. To determine whether a bond is polar or not, we're going to look up the electronegativities, and then we're going to use this table here. You won't have to memorize this table. So as you see, if the electronegativity differences are very small, END, 0 to 0.4, we're going to say that that's a nonpolar bond. The electrons are being shared equally. If it's very large, when you subtract and get 1.7 or greater, that means the difference is so great, the electrons will literally be transferred from the metal to the nonmetal. Of course, that's an ionic bond. Now, in between these, we can have sharing. Again, all of this here is sharing. Anything below 1.7 is covalent. But if they're not sharing equally, we'll say a difference after subtracting is 0.5 to 1.7. We'll call it not only covalent, but polar covalent. So this table, we're going to do a couple of these for you. If you look up the electronegativities, and again, you have to refer to that chart in your book, you would always have access to those numbers. For example, let's look at this one right here. Carbon and oxygen. We've seen that bond many times in our examples, Lewis structures and molecular geometry. So carbon-oxygen bond, is that polar or nonpolar? We already know we can guess it's covalent because it's two nonmetals. So what we're going to do is look up the electronegativities. What turns out, carbon, the electronegativity is 2.55, and the electronegativity of oxygen is 3.44. So, as we might have guessed, oxygen is further to the right on the periodic table. Oxygen is more electronegative than the carbon. If we subtract these two, we get an electronegativity difference of 0.89, if I looked at my numbers correctly. So 0.89, if we subtract the electronegativities with carbon and oxygen, we look those up in the book. The difference is 0.89, so then we look at this chart, 0.89, that puts it as a polar covalent bond. So electronegativity, 0.89, 0.89, bond polarity, we'll say polar. So the carbon-oxygen bond is polar. So when we start writing Lewis structures now, we'll say these electrons are not being shared equally. They're going to be pulled towards the oxygen. So we're going to put a partial negative here and a partial positive there. That represents a polar covalent bond. Let's look at the difference between this last one, cesium and fluorine. If you look up cesium, electronegativity for cesium is, I believe, 0.79, very low because of very low attraction for electrons. Fluorine actually has the highest of any element. It's the smallest of any of these nonmetals involved in bonding. It has the highest attraction of electrons. Okay, so if we subtract these two, we get a pretty big number because the difference is quite large. 3.919 is the electronegativity difference. We look up here, it's way into the ionic region, which we could have guessed anyway for cesium and fluoride. Because cesium is a very large atom in the bottom left of the periodic table, very low attraction for electrons. Fluoride, as I said, very small, very high attraction for electrons. So you need to go through here and complete this chart, subtract, find the electronegativities, differences, and then decide if the bond, using this chart, if the bond is polar or nonpolar. You're then going to do, and we'll do one of these for you, when we do our Lewis structures, if you recall water, like this, we had lone pairs here. This is the Lewis structure of water. So it says, show partial charges where necessary and determine if these bonds are polar. Well, if we look up hydrogen, hydrogen's electronegativity is 2.20, and oxygen, once again, was 3.44. So the difference here is 1.24. That's the electronegativity difference, 1.24. Once again, 1.24 using our chart, it means that hydrogen-oxygen bond is in this region here, it's a polar covalent bond. So it says show partial charges. So this, when I draw this line, as you recall, that means that's a shared pair of electrons. That's a single bond. Well, now we see that they're not shared equally. Oxygen is going to attract electrons more strongly. So these electrons are going to get pulled toward the oxygen. They're going to be around the oxygen more than the hydrogen. So we're going to put a partial negative around the oxygen, a partial positive here. And this bond would be the same. This is also a polar bond. It's the same type of bond. We'll put a partial positive here. We already had the partial negative there. So here is how we would show bond polarity in the water molecule. So you're going to do the Lewis structures for each of these and follow the same example and assign partial positives and partial negatives. Realize if it is a non-polar bond, and I'll give you a hint here, CH turns out to be a non-polar covalent bond. Non-polar, you're not going to show partial charges, just leave it as it is. So this is an example of how we find bond polarity.